Welcome back to the second lecture of the third week, the second lecture about machine learning of the Intelligent Systems course. 3 more to go and we are done with the new material that I dump on you. This is probably the most difficult lecture for all of us, so for you to understand and for me to give. It contains a bit of calculus, and several of you will probably have not had thought about calculus since 7 years ago, 10 years ago. I have to say that the last time I really did something with calculus was 30 years ago, so I have the more difficult part. But if there are questions, just let us try to figure them out together. Please interrupt me if there are things that are not clear, because this is an important thing to understand. There will be much more in-depth discussions about machine learning in the course next year. But I really want you to understand the general idea of these mechanisms that are nowadays sort of very state-of-the-art and really changing the world, I would say, as they are. With this technology, and in principle the ideas behind that are simple enough for you to understand in a lecture of 2 hours. So let's give it a go. Before that, I've just found this, and I always wanted to make an announcement about it, but I put a number of papers online a couple of days ago over the weekend that you might find interesting as an inspiration for your own research paper. So it is under the header, some papers for inspiration. I think it's the module writing a paper. One of them has a very, very famous author. He has already just spotted it. But the first 3 of them are real research papers, let's call them like this. So this is a Nature paper which introduces the Google methodology for the AlphaGo playing, and it's surprisingly easy to read. I would say it's not a sort of bedtime lecture, but still it's good to look at it. And there are 2 things on one is on Schnapsen and one is on card games in general. So games that are more like our game with a high a number of belief sets, so a very wide search tree. So they are quite interesting. One is about perfect information Monte Carlo sampling, which we do more or less in our RDeep knowledge, RDeep bot. And the other one is a bit older and addresses the problem as well, but I think also with PIMCs. Yeah. And then there are also some papers from last year, and that's why I had to mention Jeffrey, who's one of the authors last year. They were about a different game, so they were about the Planet Wars game, so content-wise they're not very useful for you, but I think they are quite nice and give an inspiration on how you could write it, how could you set up your research question and so forth. And in the end, these were all judged by your fellow students and by us to be good papers. So if you manage to do something similar, then that might be an indication for that you're on a good way. Yeah. So have a look at it on the Canvas page. So today is mostly about algorithms and also model selection, feature selection beforehand. Before I get into the more technical side of how to build a regression algorithm and how to find the best distinguishing model, I want to briefly have a sidestep into a different learning problem, and that's the problem of unsupervised learning and clustering. So, as I said last time, there are different learning problems, and one of them is you are given a set of classes with instances, and you want to train a model so that once you get unknown new instances, you can assign one of the classes to this new instance. In the case of unsupervised learning, we just get the instances and we don't know to which class they belong. And the task is now to order them in some kind of classes or clusters that make some sense. Yeah? I've forgotten to do this before the lecture. Can I do it in the break? And then you should have it for the second. Yeah, sorry, I've just finished them a minute ago. So can you remind me in the break so that I do it? Otherwise I'll forget. Okay, so the task is now to find things in our feature space that share properties. And if I have the classes, I know to which class they belong. So we have red ones and blue ones, specifically, particularly annotated up front. And then I get a new one and I have to say it, okay, it belongs to this class or it belongs to the other class. It's a blue one or it's a red one. And the intuition is that as it is closer to the red ones in the feature space, it probably is a red one, this pink one in the middle. Now the question is, if we don't have these classes, we can still apply some kind of nearest neighbor idea, or the neighbors, the things with the same property, that they belong to one class. So the first thing we have to do is when we get a new instance, because we don't have an explicit model that tells us to which class it belongs, to go searching for the nodes in the space, so for previous examples that have similar properties. So then we see that the pink node here is closest to one of the red ones. So then the easiest thing to do, sort of the naive way of dealing with this, is that you just say, I just give a node the label of something that I have already seen. So you just say, this is the nearest neighbor, and I just copy the label, and then this also becomes a red node. What is happening here? So now, this is a good strategy, but it's very error-prone. The strategy is I have similar classes of documents, so these would be about arts, these would be about science, and these would be about the government. And if I have, for example, text classification, or clustering of natural language text. And now I get a new instance. So this one here. And starting from the strategy of just looking at the most similar instance, I would then assign for this new document the label government, which is the label that I have for these red nodes here, because it's the closest to the red ones there. There are several problems. There's noise, so you might have one that is misclassified. And so this is an example of something that should have the label signed, but has very different properties, so ends up in the wrong part of the space. And if by any coincidence your new instance is close to this noise element, this new document will now wrongly classify as being a green one. And that's obviously not what we want. So this algorithm of just looking at the most similar object and give it the same label is very prone to errors if there is noise. Instead, you don't use the nearest neighbor algorithm, but the k-nearest neighbor algorithm, where you say, I don't look at the one object that's closest, but I look at several of them, the k nearest neighbors. It's often 3, so you look at the 3 nearest neighbor algorithm would be, which are the closest elements close to my new object in the feature space, and then I just do the majority, decide on the majority or some averaging. Yeah? So then, because I have 2 out of them are red, 1 of them is green, I would assign the label, the new class, that this is also a document about government. So that's basically the whole idea of this k-nearest neighbor that you will probably see regularly coming along, is that you represent the properties of your instances in some vector space, and you find in this vector space the closest objects, and you find the k most similar cases, and then you copy the majority label. And that is your clustering algorithm. And then you can start with some instances, individual instances, or you can start with already some example classes of several objects, and you just iteratively add your objects in some lazy way, as it's called, because you don't calculate a model up front, but you just build your classification based on the similarity of the objects in your vector space. Yeah? So that was a sort of a small side step, because I think this is important for you to have seen. And there are obviously variants about it. There is a big problem, as I said already yesterday, with these kind of approaches, because how do we now make a distinction between a good cluster and a bad cluster? We don't give it any constraints up front. We don't say that we want to cluster the domain in 3 clusters or in 5 clusters. Here we had started with these 3, science, government, and sports, or whatever it was. So that's easier, and then we can evaluate whether a particular object really belongs to the class it has been assigned to. But in principle, you don't have any a priori classes to start with. And then it might happen that your clustering algorithm gives you 2 classes or 15 classes, and which one is now better? What makes sense? And so evaluation of clustering is a big problem. And I won't use any more time here on this one, but that's sort of one of the big issues in clustering algorithms. Instead of going deeper into that, I want to spend more time on classification, in particular the model and the feature space. This was something we discussed briefly yesterday, but let's look at it in a bit more detail, because here we sort of can translate any machine learning problem in principle according to the recipe from yesterday, decide on the features, decide on the model space, and then search for the model. This is what we're going to do. So yesterday we had the problem of Bayes learning for spam filtering. So the spam problem was that we have 2 classes that we want to assign to emails that come in or texts that we have. And either they are useful documents that are ham, or they are sort of spam documents that we are not interested in. And we want our email program to automatically recognize this. So in this binary classification problem, we have 2 classes, spam or ham. And we have features that we wrote down last time, simply the words or maybe the most important words as the most important attributes. So basically if you translate this into a feature space, then we could say that we have here a binary feature space, so just features in this direction, so a word occurs or a word doesn't occur. And here it's a different word. So if you have many features, you get a many-dimensional many-dimensional space. But then you have instances that belong to some of those features, have values according to these features, and have some position in this vector space. In this case, the spam ham example might not be so useful because we have a word occurs or a word doesn't occur, but we could also count the number of occurrences. And then basically this dimension would be a natural number and the other one as well. For each of the occurrences, we would give a natural number or a number of occurrences or some more informed value. So we get, in principle, if we have 2 features to look for, we get a 2-dimensional space. And each of the points in this is a document in our case, or a training example. And basically what we're looking for is a line or some kind of geometric structure that allows us to distinguish between the blue things and the red things. So that's a linear classifier if this geometrical structure is a line. And then the model that we choose is a line, and this model is so we can choose on what kind of structure we want. And the next thing is then to find what is the best line, searching for the model, which is the best model that makes this distinction between the positive examples, the red ones, and the blue ones as robust as possible, as complete as possible, and so forth. So a linear classifier is known to have a certain property, and that is that not all of the logical problems or the full Boolean expressiveness that we have in our language can be expressed as a linear classifier. So if you have just the value being able to be true or false, if you have x or y, then the true examples are either the red point on the top, or the red point on the bottom, or the one in the middle. And then we have a linear classifier, which is just this line. And it distinguishes between the 0 values and the 1 values. So that's easy, that works. So if you later see that if we train a neural network, which is in the simplest version of a perceptron, can do linear classification, then this works. Unfortunately, for a more complex logical operator such as XOR, this is not linearly possible, linearly separable, because we now have a point here, and these two are no point. So basically, there doesn't exist a line that we can easily draw unless we do something with the features, as we see in a minute. So this is an example on the left-hand side where we can draw easily a linear classifier. On the right-hand side, we cannot, because there's no line we can draw, simple line that we can draw that gives us all the red points on the one side and the empty ones on the other side. So here we have a problem, but let's get to that in a minute. This is again the example from last time, where we have examples of people, and we have the information about the age, we have the information about the height, and we have a classification problem that we want to say whether they're women or men. And now the question is, can we sort of draw a line somewhere? That would be our classification problem in this case. Can we draw a line so that this becomes a useful classifier? Now, this works for, this visualization of the problem works for the simple case where we have a two-dimensional space. Because in a two-dimensional space, we can plot the values of the one feature on the x-axis, the other one on the y-axis. But usually, if you do text classification, for example, you have hundreds of features, and obviously our intuition fails there for drawing now the vector space, because it becomes n-dimensional. So if you go from a line, you can see that a point is a separator. If you go to 2D representation, for example, the line might be a representation of the separator. If you go to 3D, you can think of a plane. And if you go to 4D, it's usually called a hyperplane, where we can't sort of have an image with it anymore. But in a way, the idea is exactly the same, that you have a sort of separator over the 4 dimensions and more. So the examples that I will give are usually in 2-dimensional space, but are easily transferable to higher dimensions. So going back to the 2-dimensional problem, we have some blue points on one end of the feature space, we have some red ones on the other one, and we have a line that can separate these things. And then the question is, what is the best way of separating the red things and the blue things? And that becomes our machine learning problem, finding the line that separates the red from the blue ones. So the first thing in the recipe was presenting the problem as a feature in a feature space, then thinking of what kind of model do I want? Do I want a line, or do I want a curve, or whatever? And then the last thing is now, how can we now find the best one? And what is the best one in the first place? So in support vector machines, which is one of the standard machine learning methods at the moment, the idea is that you try to find this green line by finding maximally parallel lines that sort of hit the first counterexamples, and that you sort of maximize the space that is between these positive and negative examples. That is the sort of, I will get back to that in a minute. That is under the assumption that we have a line as a classifying model. But as you can see here, having a line is really a miserable choice. But the more complex your model will be, so if we say we allow any function to be the model, then its predictive power is not necessarily better. So we had this principle yesterday, the Occam's ratio. Try to find a structure for your model that is as simple as possible. And there is a very, very nice trick to do this. And that is to extend your feature space by some other properties. Yeah? So we're not yet sort of thinking of tinkering with the structure of the models, but we're still busy with looking at the feature spaces. So this is in principle the same feature space where we have the age of the people and the height and the class they are in. But we have now added information that is already available so without changing the meaning of the table and extended this to a design matrix, as it's called. And basically what you have, you just, for example, square the age, or you have you multiply age and A, and you multiply age, you square age. And this is just adding some information that the model would otherwise have to find. So your problem now turns from a two-dimensional problem into a five-dimensional problem, because you now want to have this, this function. And what happens now is that if you now plot the space back in the two-dimensional space, you get a curve. So while we still look at a five-dimensional hyperplane, so just a line in 5 dimensions, so to speak, if you reduce this to 2 dimensions again, you get a different form. So on the good side is we get a better classifier for free, and we still have the simplicity of a linear separator. We have obviously increased the feature space without sort of changing the information that we have. This is one of the things that you should do for the designing of your bots. So it might well be that if you just add the information that you have these 5 cards as features to your training set, that the separator is incapable of sort of making a good distinction between the two. But if you, for example, multiply the values of the cards, it might take the information that, oh yeah, here there must be something like 2 queens or 2 kings, and it might be able to take this dimension to separate the objects. So extending the feature space that we more or less give you in the bots for the learning towards a design matrix, as it's called, will probably increase the quality of your model very much. So this is one of the core things you should do when you build your own machine learning bot. Yeah. Here is an example why this works, or why this is really an intuitive example why this works. So if you look at this feature space here, you see that all the red, the examples for the red are in the middle, centered around the zero point, and the blue ones are around. So there's no chance for me to draw a line between these two, yeah, to separate the two. So it's not linearly separable. But if you now add the information that towards x squared plus y squared, and you plot this information, you suddenly get this geometric structure where you still have x on this axis, y on this axis, and in the third dimension, you suddenly get all the red points down and the blue points up. And suddenly, all I have to do is to add a hyperplane between the blue and the red points, on the third dimension, which will cut off all the blue ones and the red ones from each other. Yeah? So I haven't changed anything in terms of my model class. I still work with lines in many dimensions. But I still can now linearly separate these examples because I have sort of changed the feature space. And here is the example. If you just plot x to the square times x to the square times y to the square, you get all the red ones in the middle and all the blue ones on the outside. So you have a nice example of how you can even draw a linear separation by just a line. So here you would still, in this example, if you use this feature space, in your feature space you would need a hyperplane. Here you can even just use a line. So here you see a little bit the power of playing with the feature space. And as I said, this is something to experiment with. And as you might have noticed, I'm from the knowledge representation world. So my question is always, how does it work? How can we prove that it works? And so forth. So how do follow things analytically from A to B? And whenever I ask my friends in machine learning, so why do certain feature combinations work? They say, oh, they work. And so there's a lot of sort of engineering involved in order to find these ideal combinations of features. I think there is good intuition why this works, because in a way, you get rid of the positive and negative ones. So you always add the distance from 0. And that's exactly what you need here. So the squaring is usually something that helps you with negative examples and with negative values in your spaces. So there is some good intuition for squaring, for example. You should always try squaring and so forth. Then there's a slide I left in, although I don't really understand it. So, but I think you should have seen or should have heard of the kernel trick of support vector machines, because it's one of the really most important things in these systems. So what I showed you was that the support vector machine approach is you in order to find the green line that separates, ideally you have the support vectors on the right and above and below, and you have to optimize according to this. But before you do this, before you search for this, it really is valuable to try to change your feature space so that you can do this linear separation in the first place. And the kernel trick is apparently a trick that allows you to do this in a more efficient way by defining a distance function between the objects, so that you don't have to explicitly the design matrix anymore, but in a way you reduce the computation of the design matrix by giving it an explicit distance function with specific properties. And if you, for example, use edit distance, I was told, to describe the distance between objects, then this automatically helps you to define a kernel in a way that you can then do this trick of using a linear separator instead of a complex curve, without having to calculate the complex design matrix. As I said, the purpose of this slide is more to let you know that there is a lot more to the point of optimizing your features than what I've been able to tell you. And I know that next year in machine learning, this will be one of the topics that in which you will go into depth on how can you define those kernels. So distance functions that allow you to do this kernel idea of the cutting, sort of finding separators in higher dimensions in a far more efficient way. This goes up to a sort of almost absurd extreme, where you basically can add this up to an infinite feature space, which allows you to do the perfect classifier. So basically, there are types of kernels that allow you to learn these islands around the specific instances. And as you can imagine, this is sort of one bridge too far, because it is now so specific that it's what's called overfitting. It's it is too specific to your training set to be useful, because there is no chance that if you find something here, or there's a high chance that if you find something very close to these islands, that it gets a negative, the wrong classification, because the classifier is in principle is getting too complex. And there are obviously ways of dealing with this in the support vector machine community and in the problem space. So it's not that this is a sort of the wrong direction to go to, but you have to be careful about it. And things you do to avoid this overfitting is that you take some examples, for example, in the backhand, and you train your you try to avoid the overfitting with some extra examples that you check your model for. But again, this is sort of me talking about things that I really don't know that much about, and I'm pretty sure that next year you will learn much more about support vector machines, which are one of the standard models in machine learning. So we've talked about the feature space, and the feature space is really important because, as you've seen, depending on what features you have and what combinations of features you have in your design matrix, you might be able to reduce your learning problem to finding a line or a hyperplane instead of finding a very complex function. So that can be extremely useful and comes at next to no costs and is really not complicated in a way. It looks, if you look geometrically at these examples where you find a complex formula by cutting off the lower part of a geometric figure, it might look complicated, but the only thing you have to do is to add to your design matrix some interesting features. Take the squares, take combinations of the squares, and just try it out, whether your model works or not. Still, so we have the feature space, we have the model class, so I think it is mostly now acceptable, given these tricks of reducing the complexity of the models to hyperplanes or lines, given that we can play with the feature space. Let's take the decision of looking at planes or lines now. And now the question is, we have several options for putting lines between the points. Which one is the best? And this is where we get into the calculus in a minute. Let's be sure we understand the problem really. So we have our training data set, some features, some other features, and in this case a regression. So I want to give you the example with a regression problem. So you don't classify whether something is a woman or a man, but you classify a value of a function. And the idea is to learn the function so that we can if we get a new value, we can calculate the value according to this function. And the idea is that somehow we train a model, a learner, to produce a model, and the model is then the line or the hyperplane in our space. Give it a new instance, and the new instance produces a new value. So that's a regression definition, or an example, one way of formulating the regression problem, that we want to produce a new value according to some function that we learned. And this is sort of the same example we've seen before, but now the task is not to find a separator between the two, but the task is to assign a value for each of the points in the feature space. Yeah, so if we have age 50, height 160, then we might want to predict the weight or something like this. Yeah. Yeah, it doesn't say what we are going to predict. But suppose you want to predict the weight on the basis of the age and the height of a person. Yeah. Then the first idea of looking at this learning task is to find a function, this line again. And this, if it's a linear function, then it would be a line. To find this line, that allows you to predict this regression problem. Yeah. So just if you have a linear function, then you have draw a line. If you have a more complex function, you get other forms, other shapes, And this is a sort of, again, applied the same trick as I've just applied before. We have the same feature space with values, but now we have the design matrix that gives us more combinations of the features. And basically, we've changed the features so that if we draw the same line and we plot it again in 2 dimensions, we now get a curve. So there has been nothing changed in our model. The model is still a line in this multidimensional space. But when we reduce it to the original problem of age versus height as input from our examples, then we now get the structure that we want. So it's the trick of changing the dimensionality of the feature space that allows us to get more interesting, more powerful shapes, even though we are still looking for a linear classifier. So now the question is, what is a good classifier? What is a good regression algorithm? What is a good model for a regression algorithm as opposed to a bad one? And how? Because we want to find the best, so we need some notion of this model is better than the other one. And the way this is usually done is that you calculate an error function. And the error function for a training set is that you just look at the value that you know your function predicts minus the real value. Because in the training, you know the real value. So your model that you've learned predicts a value, and you just take the difference between the real prediction. And then, because otherwise the negative and positive examples would cancel each other out, you usually take, statistically proven to be a very good method is to take the square of the error. So this is the individual error is 5p of xi minus I1 is one example, the error of it. You take the square of it to avoid that the negative examples up and down cancel themselves out. And then you just sum over all of them. So the error of a test set, of a training set, is just the sum over all the examples in the set from the predicted value of your function that you've learned. Yeah, so that's, you reduce basically a plane that you have to a value using this function. Yeah, is it clear? It's part of the sort of really core bit that we're going to go into in a minute. Yeah. So depending on the choice of the line that we have, the error function changes. Yeah. So we might have one where we have a slightly steeper angle, and then the error function, or you move it up or down, and then the error function increases or decreases. Yeah. And then the search problem, as we said, in our recipe, the last of the elements of the recipe is finding, given a feature set and a model class, the best model that we have, that's possible. Yeah? So suppose we have our training set, and we just add a line, which one of them is better? Yeah? And the learning task is to find the best one. So easy is. Yeah? And each of those lines is described by 2 parameters, namely the S parameter and the B parameter. And we can now plot this S and B parameters again in a 2-dimensional space. Yeah, so now things become a bit more complicated. So if I have one function that gives us an S1 value and a B1 value, which is, so I always forget. So S is the steepness of the function, and B is the point where it goes through the 0 axis. Yeah. So so this is how you fully define your line, and so we can also just take one point in the space of S and B. And this point, the red point now, denotes exactly one line, one separator. Yeah? So in this space of S and B, we can identify all the possible lines that separate our examples, right? Yeah. So then we get to this, which is now plotting the error rate with respect to each of our options of each of our lines that we can draw. So basically, here you have the b-axis, here you have the s-axis. So these points down here, they are all our possible models. Yeah? And then basically for each of the points, I plot on the third dimension, I plot the error rate. Yeah? So for one training set, I have for all the possible lines, I can calculate the error rate. And this point then has some value in my error space. Yeah, is that clear? This is sort of, we're getting to the crunch point, which is a good moment to be at the crunch point of a lecture. And now the task, what is the task now of our machine learning algorithm? What did I just say? What is, yeah? Exactly, finding the one object down here, the point here, which has the minimal value of the error function. Yeah? In other words, if you look at the geometric structure, and remember that we are here in two-dimensional space only, so that gets more complicated, but don't worry about that now. So if we are in the simple space, it's the lowest point of this shape that we're looking for. So we're looking at this green point down here, which has the property that it is optimal in the sense that the error function is minimal. It's not necessarily nil, but it's minimal. And this point refers to a line, a separator, that is optimal because it's the best line we can find. It's the best model with respect to minimizing the error function. So our task now for the second half of this lecture is how can we find in this, yeah? This is what we're going to do in the second half. Okay, see you. See you back at 12, please, yeah?